So now in this class we'll be seeing switching modulator. So this switching modulator is shown in this figure. At the input side we have message signal and carrier signal. So as we know, for a modulator we have two inputs, one message signal and carrier signal, and the output will be modulated signal. So this simple circuit consists of a diode and a resistor. So the output voltage is measured across this resistor RL. So here in this switching modulator, we assume that this carrier wave is having larger amplitude when compared to the message signal. That means the value of AC is much high when compared to the value of AM. And also we assume that the diode is ideal, means it will act as an ideal switch. That is, when it is forward biased, it will be having zero impedance, and hence it will act as a short circuit. And when it is reverse biased, it will be having infinite impedance and hence act as a open circuit. So this figure shows the ideal diode characteristics. So when V2, this output voltage is plotted across this input voltage, we will be having a straight line of slope 1. So from this figure we can see that V1 is the sum of message signal and carrier signal. So V1 is equal to m of t plus AC cos 2 pi fct. So as said, as we are assuming carrier signal is dominating, the polarity of V1 of t will also be decided by the polarity of the carrier. So since we are assuming that this carrier is more dominating when compared to the message signal, sign or polarity of this V1 of t will be depending only on the carrier. So for that we can see some examples over here. So let's say that AM value is, that is amplitude of message signal is 0.5 and carrier is 5, then their sum will be 5.5. Let's say that AM is 0.2 and AC is -2. So here we are taking AC as negative value. We can see that their sum is also negative. And in the case when we consider AM is negative and AC is positive, again the output is positive. So here we can observe that the polarity of V1 of t is same as the polarity of the carrier amplitude. So from this what we can say is that this diode will be in forward bias when V1 of t is positive, and this diode will be reverse biased when this V1 of t is negative. So since V1 of t is mainly dominated by carrier signal, so if the carrier signal is positive, diode will be forward biased, and if the carrier signal is negative, then the diode is reverse biased. So for the positive half cycle of the carrier, V1 of t is positive and the diode is on. Since the diode is on, V2 will be exactly the input voltage, that is V1 of t. And for the negative half cycle, V1 of t becomes negative and hence this diode will be switched off because it is reverse biased. So since it is off, there will not be any voltage drop across this resistor, and hence V2 will be 0. So now if we combine these two equations, we can write V2 of t as V1 of t times Gp of t, where Gp of t is the periodic signal whose period should be exactly equal to the carrier signal. So why we are taking this as a periodic signal with period fc? Because for positive half cycle of carrier, Gp of t should be 1, and for the negative half cycle, Gp of t should be 0. And since it is periodic signal, its period should be exactly equal to the carrier signal. So the carrier we are using is cos signal. So cos signal will look something like this. So this will be the time period of the carrier. So at 0, it will be having maximum amplitude of 1. So it will be repeating every time period Tc. So this one will be Tc by 2, and this one will be Tc by 4. So now if we take this periodic signal Gp of t, so this is the carrier signal. So now if we plot this Gp of t, so on this carrier will be like this. So now as I said, for the positive half cycle of the carrier, so for this part Gp of t should be 1. So that means these values, for these values, that is from minus Tc by 4 to Tc by 4. So this Gp of t will be 1. That is for positive half cycle. So again for this negative half cycle, so from this part to this part, the signal will be 0. And again here the amplitude will be 1. So this will be centered at Tc. Similarly here on the negative side, it will be minus Tc. This is minus Tc by 2 and this will be Tc by 2. So this is how we have plotted the signal Gp of t. So it is a periodic signal which is having an amplitude of 1 for the positive half cycle of the carrier and 0 amplitude for the negative half cycle of the carrier. So now if you observe this, this is an even signal since it is symmetric over this y-axis. So for the positive values and for negative values, the amplitude is same. So here this Gp of t is an even signal. So we all know that this periodic signals can be represented by using Fourier series. So this is the periodic signal. So from minus Tc by 4 to Tc by 4, it will be having 1, and for the remaining values, it will be 0. So by using Fourier series expansion, this can be expressed as a0 by 2 plus sigma n equal to 1 to infinity an cos n omega ct plus bn sin n omega ct. So this one you have already studied in Fourier series expansion. So now we need to calculate these values a0, an and bn. So a0 is the actual definition is 1 by t times minus t to t Gp of t dt. So this is the actual definition for a0, but since it is an even signal, so from minus t to t, it will be the same signal will be repeated. So what we can do is, instead of calculating this from minus t to t, we can change it from minus t by 2 to t by 2. Here it is Tc by 2 to Tc by 2. And we can double this value. So it will become 2 by Tc. So instead of calculating this from minus Tc to Tc, we are calculating only for the half of the period, that is from minus Tc by 2 to Tc by 2, and we are multiplying it by 2 because the same signal is repeated periodically. So a0 will be 2 by Tc integral minus Tc by 2 to Tc by 2 Gp of t dt. So if we simplify this, it will be 2 by Tc integral. So here from minus Tc by 2 to minus Tc by 4, the amplitude is 0. So here the limit becomes minus Tc by 4 to Tc by 4, and the amplitude is 1. So 1 dt. So this one will be 2 by Tc times Tc by 4 minus of minus Tc by 4. So this will be 2 Tc by 2 and 2 by Tc. When it will be multiplied with 2 by Tc, the amplitude will, the a0 value will be 1. Similarly, the value of an will be 2 by Tc times integral minus Tc by 2 to Tc by 2 Gp of t cos n omega ct dt. So if we substitute the value of Gp, so again the limit becomes minus Tc by 4 to Tc by 4. Gp of t is 1, so it will be cos n omega ct dt. So it will be 2 by Tc. So integral of cos signal will be sin n omega ct divided by this part n omega c, and the limits are from minus Tc by 4 to Tc by 4. So here the value will be 2 by n omega c Tc times sin n omega c Tc by 4 minus of sin again minus n omega c Tc by 4. And we know that omega c is equal to 2 pi fc. So omega c Tc will be 2 pi fc times Tc. So we know that Tc is equal to 1 by fc. So these will be cancelled out, and omega c Tc will be equal to 2 by pi. Sorry, 2 pi. So this one will be 2 by n into 2 pi sine. So this omega c Tc will be 2 pi. So it will be sine n 2 pi by 4. So minus sine of minus theta will be minus sine theta. So it will become sine n 2 pi by 4. So which will be equal to, so this 2 will be cancelled out, and we have 1 by n pi, and here this will be 2 sine n pi by 2. So 2 pi by 4 will be pi by 2, and as we are having two terms, it will be 2 sine n pi by 2. So the value of an is 2 by n pi sine n pi by 2. So we have calculated the value of a naught, we have calculated the an, and the value of bn will be 0, since Gp of t is an even signal. So for even signals, bn will always be 0. So this is the Fourier series expansion. So the same expressions have been written in these slides. So a naught will be 2 by Tc integral minus Tc by 2 to Tc by 2 Gp of t dt. So since this Gp of t is defined for only these values from minus Tc by 4 to Tc by 4, so a naught value will be 1. Similarly, we have calculated the value of an, and by using this omega c Tc is equal to 2 pi, we get the value of an as 2 by n pi sine n pi by 2. And for even signal, bn will be 0. So now if we substitute these values a naught and an, bn values in the Fourier series expansion, we get this one. So Gp of t is equal to a naught by 2. So since a naught is 1, so 1 by 2 plus sigma n equal to 1 to infinity. This is an value 2 by n pi sine n pi by 2 into cos n omega ct. So Gp of t will be a naught by 2, which is 1 by 2 plus sigma n equal to 1 to infinity an value is 2 by n pi sine n pi by 2. So this is the value of an into cos n omega ct. So now if we expand this equation, we get 1 by 2 plus. So we can take this 2 by pi common. So 2 by pi times. So when n equal to 1, this one will be 1 by n sine pi by 2. Sine pi by 2 cos omega ct plus for n equal to 2, this one will be 1 by 2 sine 2 pi by 2, which will be pi cos 2 omega ct plus 1 by 3 sine 3 pi by 2 cos 3 omega ct plus 1 by 4 sine 4 pi by 2 will be 2 pi cos 4 omega ct plus 1 by 5 sine 5 pi by 2 cos 5 omega ct and so on. So this one will be 1 by 2 plus 2 by pi so this sine 90 will be 1, so this one will be cos omega ct plus the sine pi will be 0, so this term will be 0 plus 1 by 3 sine 3 pi by 2 will be minus 1 cos 3 omega ct plus again this sine 2 pi will be 0 plus 1 by 5 sine 5 pi by 2 will be 1 cos 5 omega ct and so on. So now this Gp of t can be written as 1 by 2 plus 2 by pi cos omega ct minus 1 by 3 cos 3 omega ct plus 1 by 5 cos 5 omega ct and minus 1 by 7 and so on. These terms will be continued. So this is the final expression that we have obtained by using Fourier series expansion. Now we have obtained the expression for Gp of t and we know the value of V1 of t. So now V2 of t can be obtained by multiplying this V1 of t and Gp of t. So V2 of t will be equal to V1 of t times this periodic signal Gp of t. So V1 is nothing but the sum of message signal and carrier signal, and this is the expression for Gp of t which we have obtained using Fourier series expansion. So now if we multiply this message signal with all these terms, we get mt by 2 plus 2 by pi m of t cos omega ct and so on. These are all. We have many other terms which are not required, and when we multiply this AC cos omega ct with all these values, we get the first term will be AC cos omega ct by 2 and second term will be 2 by pi AC. Since we are having two cos terms, it will be cos square omega ct and plus so on. So now if we observe this equation, so here the first term, the frequency component will be Fm, and here the frequency component, since it is the product of message signal and carrier signal. So here the frequency components will be Fc plus or minus Fm. And here the frequency component will be Fc. And here, since it is cos square omega ct, so here the frequency component will be 2 into Fc. So now, so similar to the square law modulator, now we pass this V2 of t through a band pass filter, which is tuned to the frequency Fc. So when this is passed through a band pass filter, so only these two terms which are having frequencies around Fc will be passed. If we write these two terms on one side, so we get, and so we can take this AC by 2 cos omega ct common from these terms. So since cos omega ct is already there in this term, so since AC by 2 is not there here, so you can multiply it with 2 by AC. So it will be AC by 2 into 1 plus 2 by AC times 2mt by into cos omega ct, plus remaining all the terms will be unwanted terms. So the final equation will be AC by 2 into 1 plus 4 by pi AC m of t into cos 2 pi fct plus unwanted terms. So if we observe this, this is of the form AC into 1 plus Ka m of t cos 2 pi fct. So this is the standard AM wave with amplitude sensitivity Ka is equal to 4 by pi AC. And these unwanted terms can be removed by using a bandpass filter, similar to the square law modulator. So this is how an AM wave is generated by using this switching modulator. So this is called switching modulator because diode will be continuously switched between on and off states. So hence the name switching modulator.